In March 2026, exploration company Ocean Infinity concluded the most technologically advanced search for Malaysia Airlines Flight 370 to date. After 151 days at sea, mapping over 140,000 square kilometers, the mission ended with zero physical recovery. The operation operated at a staggering scale. Fleets of autonomous underwater vehicles scanned the abyssal plain, navigating through a region of the planet that remains more poorly mapped than the surface of Mars. This creates a unique forensic deadlock. MH370 is the most physically elusive object in the history of aviation, yet its flight path is simultaneously the most modeled and data-dense event in aerospace history. Finding the aircraft requires deconstructing the sensor data fusion used to track it, specifically the repurposing of unintended satellite artifacts from Inmarsat and the analysis of radio frequency anomalies through WSPR-net. Locating the wreckage has become an engineering challenge, a task of resolving the specific discrepancies between these two distinct forensic methodologies. Standard air traffic control relies on active radar networks. While these systems provide a safety net over land and coastal waters, they terminate at the edge of the deep ocean, leaving massive segments of the flight path in a telemetry dark zone. When the primary transponders were disabled, the plane effectively vanished from civilian and military tracking screens, forcing investigators to look for signals never intended for positioning. In the absence of GPS or radar, engineers began exploiting automated handshake signals, unintended pings between the aircraft's onboard satellite terminal and a geostationary Inmarsat satellite. This deliberate blinding of the aircraft eventually necessitated a radical shift in forensic radio frequency analysis. The first key metric is burst timing offset, or BTO. This is a microsecond-level measurement of the time it takes a signal to travel between the aircraft and the satellite. Early official models relied on just 17 samples taken while the plane was on the ground. However, signals at the airport are highly susceptible to multipath errors, radio waves reflecting off hangars or nearby equipment, which skews the timing data. The independent group utilized all 497 airborne records. By focusing on data gathered after takeoff, specifically clusters 5 through 8, they avoided signal jitter. They calibrated this data against known positions recorded before 1707 UTC, verifying the timing against a confirmed physical location. This process established a precise mathematical constant for the flight, a BTO bias of negative 495,663 microseconds. Converting this time delay into distance creates the seventh arc, a specific, equidistant ping ring that defines exactly how far the aircraft was from the satellite during its final transmission. This rigorous calibration eliminated millions of square miles of potential search area, locking the flight's end phase to a single mathematically defined arc. While BTO provides distance, burst frequency offset, or BFO, measures the Doppler shift, the way the satellite signals frequency changes based on the aircraft's motion. BFO data constrains the aircraft's speed, its heading, and its vertical rate. At 0019, the final handshakes recorded a massive frequency drop, falling from 182 Hz to -2 in 8 seconds.
The terminal compensates for horizontal speed, meaning this shift can only be explained by a rapid change in vertical velocity. The calculated rate of descent at the end of the flight is approximately 15,700 feet per minute, a vertical speed of 155 knots. This indicates a gravity-accelerated, tight spiral dive with a radius of less than 1 nautical mile. This terminal BFO data effectively rules out a long, controlled glide. The aircraft likely impacted the water directly on or immediately inside the seventh arc. To find where along that arc the plane ended up, investigators turned to thermodynamics, calculating exactly how far the Boeing 777 could fly based on its initial fuel load and takeoff mass. The model assumes the aircraft maintained a long-range cruise at 35,000 feet. Researchers then added real-world variables, such as non-standard atmospheric temperatures from NOAA global data, which directly affect engine efficiency and fuel burn. They also applied a 3% performance degradation allowance for the specific Rolls-Royce Trent 892B engines, further refining the modeled fuel flow. By plotting this fuel exhaustion curve against the BTO telemetry, a specific geographic intersection emerges. This model places the most probable endpoint at 37.71 degrees south, 88.75 degrees east. Fusing radio propagation delays with thermodynamic flow rates provided the baseline for the massive physical searches conducted by Ocean Infinity. However, a different methodology emerged that challenges these predictive fuel models: WhisperNet. The Weak Signal Propagation Reporter is a global network of low-power amateur radio signals that form a multi-static mesh across the planet. When a Boeing 777 passes through one of these radio links, its metallic airframe scatters the signal. WSPR-net receivers integrate signals over 110 seconds. This allows researchers to identify specific spikes in the signal-to-noise ratio exceeding a standard deviation threshold. By tracking anomalies in signal strength and frequency drift, investigators map where an aircraft disturbed the mesh. The dataset is extensive. Researchers have identified 313 signal anomalies along the flight path across 130 distinct points in time. Unlike the straight-line autopilot assumptions of earlier models, the WSPR-net data tracks a dynamic flight path involving deliberate changes in speed and heading. This evidence shifts the target zone significantly north, to a 30-kilometer radius centered at 29.128 degrees south, 99.934 degrees east. These two models are in direct conflict. To the south sits the BTO fuel zone, to the north is the WSPR-net pinpoint. The 2026 search focused its massive mission on the southern corridor, 45 nautical miles wide. This operation effectively exhausted the search area suggested by the older BTO fuel models, while the WSPR-net target remained unsearched. This highlights the tension between sophisticated statistical forensics and the physical reality of the deep ocean. Ocean Infinity has described the scale of this challenge as almost impossible to comprehend, even with the most advanced robotics and modeling available. We have the telemetry to track invisible radio anomalies through the ionosphere, yet converting these refined coordinates into a physical recovery remains stalled by institutional friction and the sheer vastness of the Southern Ocean.